Hey there, I am Kiran. I welcome you to our presentation on our project, a visual linguistic AI pipeline for improvised image analysis. My team for this project also includes Adithyan Rajesh, Salwan Subair, and Sreehari. Together, we have engineered a system that combines the visual power of computer vision with the descriptive intelligence of natural language processing. To build such an ambitious system, we needed a robust foundation. To achieve this, we first needed robust training data. We began with the well-established Flickr 8K dataset. This dataset is our foundational truth for image captioning, providing us with over 8,000 images, each rigorously labelled with 5 distinct human-generated captions. This gives us 40,000 linguistic examples to train on, teaching our model that there isn't just one way to describe a scene. There are many valid narratives. Our data pre-processing pipeline cleans and formats this massive dataset, preparing it for the complex training tasks ahead. The core challenge lies in translating visual features into sequential text. This isn't just classification, it's generation. Our solution addresses this by using a vision encoder-decoder model architecture. Think of this system as a translator with 2 specialized parts. The encoder consumes the input, the image, and distills it down into a dense, numerical representation. The decoder then takes that abstract thought and expands it into a coherent, descriptive sentence. This meticulous setup ensures seamless data flow between the 2 very different model types. And with that, let's pass it over to our optimizer to explain how we trained this complex machine.
Our training started with careful data handling, a crucial first step for any robust machine learning model. We implemented the Flickr 8K dataset custom class, which is fundamental to the entire training process, ensuring data integrity and accessibility. This class handles the image and caption pair retrieval, ensuring robust loading by including error handling to skip corrupt images, a vital feature for real-world datasets. It performs 2 key operations. First, it converts the image to the Viteredi pixel values, standardizing the visual input for the model. Second, it uses the tokenizer to convert the caption into numerical input IDs, translating human language into a machine-readable format. Crucially, it sets the label's parameter, replacing the padding tokens with -100, a technique essential for accurate model training. This ensures that the model's loss function correctly ignores the padding tokens during backpropagation, preventing irrelevant data from influencing the learning process. Ultimately, this leads to more focused and accurate training, optimizing the model's ability to understand and generate image captions effectively.
Our training optimization was paramount in developing our seek-to-seek model. We leveraged seek-to-seek training arguments to maximize data throughput, primarily by increasing the batch size. Critically, we enabled FP16 equals true for mixed precision training. This mixed precision approach was essential, effectively having the GPU memory requirement. It also significantly speeds up training time, allowing us to train a larger, more powerful model on limited resources. For evaluation, we bypassed simple accuracy in favor of the more nuanced Rouge metric. We specifically optimized for Rougel, which is the gold standard for linguistic quality. This metric rewards the model for maintaining overall sentence structure and flow, ensuring our captions are fluent, not just lists of words. To guarantee stability, we implemented early stopping to halt training if the Rougel score stalled, preventing overfitting. We also enforced load_best_model_and equals true to ensure only the highest performing version from the entire run was saved permanently. This optimized, highly accurate model was then compressed into a self-contained, deployable zip file, ready for practical application.
To achieve a professional, production-ready result for captions, we implemented a 3-stage inference pipeline. The first stage involves our VIT-GPT-2 model generating a raw caption, which can sometimes be rambling or ungrammatical. To fix this, we aggressively filter the text by stripping punctuation, converting to lowercase, and using an expanded list of stop words. More importantly, a basic stemming check prevents redundant words, boiling the rambling caption down to a tight, 6-word maximum list of crucial concepts. This keyword list becomes the clean input for the next stage, where we eliminate grammar issues using a dedicated T5-based grammar correction model. The T5 model treats grammar correction as a sequence-to-sequence translation task, taking fragmented input and translating it into a fluent, grammatically correct sentence. Beyond generating a description, we want our system to visually verify its work, which is where object detection comes in. Our object detector validates the captioning model's claims and provides concrete, labeled bounding boxes to the user, building trust through transparency. We use the faster RCNN with a ResNet 50 FPN backbone, a leading architecture known for its balance of speed and accuracy, initialized on the massive COCO dataset. To clean up raw object detection output, we set a high confidence threshold and use non-max suppression, pruning overlapping boxes to ensure a clean, accurate visual output.
In summary, our inference phase is designed for robust quality control, featuring a powerful 3-part process. Firstly, to clean up the raw output, captions are aggressively filtered by removing stop words and performing a stemming check to produce only concise keywords. Secondly, linguistic integrity is assured by a separate T5 grammar doctor, which takes these keywords and reconstructs them into a grammatically flawless final sentence. Finally, visual verification is achieved through the faster RCNN object detector, which independently confirms the existence and location of the objects mentioned in the caption. This detection output is then processed using non-max suppression to eliminate overlapping boxes, ensuring the final visual plot is clean, reliable, and entirely transparent to the user. Our pipeline guarantees the final output is accurate, polished, and visually confirmed. This rigorous pipeline leads us directly to the final results. I will now pass the torch to Sreehari, who will showcase the final output, analyze the case studies, and conclude our presentation.
Raw object detection output can be quite messy. A single object often ends up with multiple overlapping bounding boxes, and this can confuse the final visualization. To fix this, our system applies 2 layers of filtering. First, we keep only detections with a confidence score above 60%. Then we apply something called non-max suppression, or NMS. This algorithm removes the extra overlapping boxes and keeps only the one with the highest confidence. After NMS, the output becomes clean, clear, and easy to understand. This ensures that only the most accurate and most relevant objects stay visible in the final image. The last stage of the pipeline is where everything comes together. We use Matplotlib to create a complete visual output. The original image is displayed, and the refined bounding boxes from the NMS step are drawn using a clean cyan outline. Each box is labelled using the COCO category name so viewers immediately know what was detected. A key part of this final visualization is the caption. After grammar correction, the improved caption is placed at the top as the main title. This lets viewers instantly compare what the model detected with what the caption actually describes. This project shows what's possible when multiple AI components are combined into one system. We used a GPT-2 caption generator, a T5 grammar corrector, and a faster RCNN detector, all working together. The models run efficiently thanks to techniques like FP16 training and ROUG-EL evaluation. For future work, we want to add a relationship detection model that understands actions like running or throwing. We are also exploring multimodal retrieval that automatically finds matching B-roll or reference clips based on the caption. This would turn the project from static image analysis into an intelligent video creation pipeline. Welcome to an exploration of our visual linguistic AI pipeline, an advanced framework integrating computer vision and natural language processing. This pipeline generates descriptive captions for images, enabling machines to interpret and articulate visual scenes in human-like language. Let's look at a real example from our notebook. In this test image, the caption model produced a rough descriptive phrase. Our filtering step extracted meaningful keywords, something like person, dog, field. The T5 model then turned those keywords into a smooth, human-like sentence such as, a person is walking a dog in a field. At the same time, faster RCNN detected clear bounding boxes for both the person and the dog. When these outputs are shown together, we get a reliable and transparent representation of what the model sees and how it interprets the scene. This project provides a powerful foundation for building advanced visual AI applications. You can access the full notebook, training data and inference code in our repository. Our model is available on Hugging Face Under, Kiran Feb 05/Flickr 8K-caption-model. We invite you to test it, use it, and even contribute to improving it. Thank you for exploring our visual linguistic AI pipeline. We appreciate your time, and we're happy to take any questions.